anyways, I'll be out there at 10 a.m. tomorrow, giving the intro to the lab. I'll record it and post it on my YouTube channel. No one's required to attend as normal, but just letting you know. I'll also be logging in. Excuse me. I'll also be logging in to my 5:30 p.m. class. I'll and log in by 5 p.m. so that y'all can have a possibly another 30 minutes beforehand. So if you actually wish to, you can show up. My 5:30 on Thursday class. Show up as early as 5 and on Thursdays, every Thursday for that matter, and that'll be another chance for you to ask questions if you have any regarding lab, lecture, anything really. So. With that being said, let's go ahead and get started. I'm trying to knock out chapter two. So we pretty much got through the parts where I showed you how to integrate a acceleration, uh, and that was kind of important. So we needed to be able to do that because if I give you an acceleration that's a constant, that's the derivation that I did to give you the kinematic equation. Excuse me, to arrive at the kinematic equations we'll use throughout the whole semester. But another part of this chapter is you guys being able to be given an acceleration as a function of time and doing the exact same process that I did to derive v equals v0 plus at, and then from that setting v equal to uh, dx dt, and then integrating that to get 1/2 at squared plus v0t plus x0. So that's another sort of thing you did. In the case of us, I actually did that by doing indefinite integrals, but you could do definite integrals as well, which is what I did when I did the integration of a as a function of time. I think I used 3t squared plus 4 is equal to a of t, and I set that equal to dv dt, and then I gave you the initial conditions, the initial velocity. I think I said the initial velocity was 1 meter per second or 2 meters per second or something, and the initial position was 0.00 meters. Uh, Upon using those initial conditions, I could just integrate 3t squared plus 4 is equal to dv dt. That would give me something like the v equals v0 at, but it's different because the acceleration is not a constant. And then using the initial condition, that actually allowed me to figure out the whole v of t. Then I set that v of t equal to dx dt, integrate that, and that gave me an equivalent expression to x equals 1/2 at squared. But again, this is for a non-constant acceleration. So that's another type of problem you should be able to do. So I'll give you a recap of exactly what those equations are that we derived using the indefinite integral. Oh, my internet connection's unstable. Let's see what's going on. What internet am I on? Looks like that's fine. Let's see what internet my iPad's on. The internet on my iPad is the same one. Okay. I don't know why I'm yawning. All of a sudden, it's hitting me. What I'm going to do real quick is I'm going to copy a blank page, copy page, and I'm going to paste it before this so I can put an actual problem, uh, or give a recap before I start the first problem. I'll paste before. Okay, so let me go ahead and share my iPad screen with you folks, and we'll get started on finishing up chapter two. Uh, Everybody, in case you came in after I told this is a time where you want to go ahead and chat me your first and last name, and you can also ask me a question before I get started. Before I get started, if you like. That's not good. All right, so just to recap, what we came up with from our kinematics was I gave you a definition of average speed, and the average speed was S bar is equal to distance divided by time taken. Now that's supposed to mean the distance traveled divided by the time taken during that travel. That's entirely different from the displacement, which I'm going to show you as well. The average velocity is displacement divided by time taken. And the displacement, remember, I said you can treat it like an arrow because it is technically a vector quantity. And what it would be, the displacement, is a vector that points from your initial position when you first start studying the motion to your final position when you want to stop studying the motion. If you imagine that displacement being a vector, an arrow that goes from that initial point to that final point, then the length of that arrow is called the displacement. That's the magnitude of the displacement. And the direction is the actual direction of the displacement vector, which again we'll learn in chapter 3. So it's a little bit more than just saying it's the distance away from where you first started because it actually is a vector quantity. So that is your displacement versus time. We found out that that could be written as delta x over delta t, and that's perfectly acceptable. And remember, delta, unless otherwise specified, delta is supposed to be final minus initial, so that's x final minus x initial over t final minus t initial. We also found the instantaneous velocity, v instantaneous, which we could also write as v of t, and that was the same thing as the average velocity, but we managed to convert it to instantaneous by taking the limit as delta t approached zero of delta x over delta t, and that, of course, from our knowledge of calculus, is just dx dt. Then we introduced the average acceleration, and that turned out to be basically delta v over delta t. And of course, that means v final minus v initial over t final minus t initial. I want to remind you guys that there's a lot of different ways of writing v final and v initial. So one way we could, for instance, write this is we could write v minus v zero. That's the same thing as v final minus v initial. We could also write this over just plain t or delta t or t final minus t initial, but I'm going to put it like this. And just one more way, v minus v0 over t is another way we could write it. And I'm making a bigger point that you're going to see in a second. Now, we could convert that to an instantaneous acceleration, which is a of t. And the way we do that is again by introducing a limit as delta t approaches zero of delta v over delta t. And that, of course, turns out to be dv dt, the instantaneous rate of change or the derivative of velocity with respect to time. But the velocity was already dx dt, so this is also d2x over dt squared. Okay. So when we allowed a to be a constant, so if we assume a equals a constant, then a bar is equal to a equals some number, and we were able to find out that we get v is equal to v0 plus at. Notice if you look at this version right here of a bar, if you actually solve this for v, you'll get exactly this expression. The only difference being that the a would have a bar over it instead of that. Okay, so it is technically a new equation, but it's very similar to the old one. That being said, it's still one of the kinematic equations, but it's only valid when a is a constant. If you stuck a bar over there, then it's not valid at all times. Now, what we did after we integrated a equals dx or dv dt, we got this v0 plus at equals v of t. Then we said, okay, I'm going to take that v, which is equal to v0 plus at. I'm going to set that on the left-hand side of an equal symbol, and then on the right-hand side is going to be a dx dt, and I integrated that. When I integrated that, I got x. Ooh, let's write with the pen. I got x was equal to 1/2 a t squared plus v0 t plus x0. And then if I took that first equation, the v equals v0 plus at, the first one for a constant acceleration, if I solve that for time, I could plug that into the second equation, the x equals 1 half at squared plus v0t plus x0 equation. And when I did that, I ended up coming up with this result, v squared is equal to v0 squared plus 2a times x minus x0. I will say that it's very common for me and for us in general in terms of physics to just call this quantity delta x sometimes to save us a little trouble, because to be honest with you, you can always set your coordinate system such that x0 is equal to 0, in which case then that delta x just becomes x. So that's certainly reasonable as well. Now there's one more equation. I didn't really derive this one for you in any sense, but it does come in handy, and that is the average velocity is equal to v plus v1 over 2. But again, all these are only true in the event that a is a constant. So these ones below that sentence, if we assume a equals a constant, those are only true when a is equal to a constant. But those are our kinematic equations. Those are what we're going to use. Those are what you're allowed to use. And I did tell you that sometimes certain instructors won't let you use the v squared equals v0 squared plus 2a delta x. Sometimes they just don't allow you to do that because that's not a vector equation. You could do something like this as a vector, but it would take something called a dot product, or also called a scalar product, to get something like it. And even then, you'd still have to take some physical make some physical argument as to whether the velocity, if you're solving for velocity or velocity initial, either one, you'd have to take a square root. And you'd have to decide whether it's a positive square root or a negative square root. So there's some ambiguity built into it that relies on your knowledge of and understanding of physics in first principles. So there's a lot of reasons not necessarily to use it, but by all means use all of them. Okay, just remember when they're valid. I will tell you that the definition of average velocity also gives us this nice little equation, x is equal to x0 plus v bar t, and that's true at all times. So if you happen to have the acceleration being a constant, then you could use this to calculate v bar, and then you could plug that v bar in here, and that would give you the distance traveled vt after any amount of time t, or it could give you your new position x0 plus v bar t for any distance and time of travel, and assuming that you knew the initial position. So those are our kinematic equations. We'll use them over and over again. Sometimes I number them and refer back to them, but that requires me to remember what order I put them in and that sort of thing. So I'll just usually write them down when we go to use them. Now that we have recapped that, remember that process that I did in deriving these four equations, or the first three of these equations at the bottom. That is something you're expected to be able to do, whether it be, like I said, an indefinite integral, and then using the initial conditions to figure out what the constants of integration are, and then or the other way is to actually solve the differential equation using the initial conditions and using definite integrals. So you never have a constant integration, but by doing definite integrals, you end up having the v0 and the x0 come out initially all by itself. Okay. Anybody have any questions on any of that? On any of these equations or anything?
Looks like there's a couple of questions in the chat, potentially.
Okay. Yeah, glad you let me know that because I did not put the chat up yet for this. Okay, there you go. Yes, someone asked about a formula sheet for the exam. You're not allowed to bring a formula sheet in the traditional sense. You're allowed to bring my equation sheet. So if you look in the helpful documents and links, there's an equation sheet in there. But the easiest way is just look at your practice test one. If you scroll down to the bottom of practice test one, or the online test one, which of course is due by Sunday afternoon, if you look at that, that actually has the equation sheet in it, and it has all the extra data that you might need that will be provided to you when you take a test. So if you look at the practice test and the online test, you'll get a feel for exactly what's allowed to you for you. Okay. Benjamin, do you have another question?
Yeah, I had a question, Professor. So for the exams, is it due by the first? We come to the campus to take it, or
No, this is an online test, and that means you're allowed, not only are you allowed to take it at home on your own, but you're allowed to take it at home on your own with open books, open notes. You can even do Google searches. The only thing that I'm
uh,
trying to prevent you guys from doing when you take this online, oh, by the way, you're also allowed multiple attempts. I usually allow 3 attempts, and only your highest score will count. But in addition to that, the only thing I really trying not to allow you to do is I don't want you guys to have the ability to talk to someone that's already seen the test and get help from them. So I try to
okay.
word that by saying you're allowed all this stuff, but you can't talk to or you can't look at a website or a document or anything that was made after the day I opened the test. So that's the rule I try to use. But I'm allowing you to, do a Google search for the individual questions. You have a limited amount of time, and when I used to allow you to go over that time, that would take off huge points for going over the time. But now I just set it up where you have a fixed amount of time, and if you look up too many of them, you'll run out of time too quickly.
All right. I got another question. Like the
Mhm.
due dates on the Pearson, it's like they're really close. It's like we have work due almost every 2 days or something like that. I was looking at it yesterday.
Yes, I just changed some more of those dates to that they sort of stack up a little bit, but really what matters is the chapter that you're covering homework. So those are only the due dates that matter. So far, we're still working in chapter two, haven't started chapter three, but just before I came into class today, I went ahead and changed the due date for chapter two homeworks and chapter three homeworks. So they got a little bit more space between them.
All right. Thank you.
Okay, no problem. Yeah, remember, guys, if there's ever a due date for a chapter, it'll automatically just pop up because mastering just does some random stuff with the dates in some sense. Often what'll happen is you might see something where chapter seven is due like tomorrow, and you're like, oh no, I don't know if I need to do that. Well, no, you should know immediately whether you need to do that because if I haven't started chapter seven, then that date is irrelevant. So I'm never going to give you a homework that is due before I even started the chapter. Once I start the chapter, it's my job to make sure I change the due date for that chapter homework. But until then, it's your job to know that the due dates don't matter. Okay? So keep that in mind. Hopefully that'll help. And I'm not doing that to try to weasel out of my responsibilities. I'm just trying to get you guys out of the fear of saying, "Oh my God, I got to stay up till 2 o'clock in the morning and do this homework that I've never covered before." I'm not that mean. I'm usually pretty nice, and I work hard to help you guys understand. So, all right, let's go on now. Here's a version of a problem that your book has. It says if a plane needs to reach 27.8 meters per second before it can lift off, and the plane has a maximum acceleration of 2 meters per second every second, is a 150-meter runway long enough? And B, if not, how long of a runway is required? So that's the questions we're trying to ask. I've sort of paraphrased uh, the problems in the book. I'm pretty sure paraphrasing is not copyright valid, so hopefully they don't come get me for this. But I'm trying to be as quick as possible as I can without having to waste a whole lot of time typing stuff and making up new questions. But anyways, so the problem we're trying to work is this one, and what we're given here is the fact that the plane will start from rest and it will try to reach 27.8 meters per second, which, by the way, 27.8 meters per second is about 100 kilometers per hour, and that's about 60 miles per hour. So, what they're saying is this airplane needs to reach 60 miles per hour to be able to lift off. And if the runway is not long enough, like, there's a ditch or a tree there, that's going to be a bad day for airplane taking off. So, what we need to think about, and this is largely what you're doing when you first start physics, is you're trying to learn from my lectures and my discussions and my derivations what symbols correspond to what quantities. And usually the biggest indicator of that is the units. Like right here, you see 27.8. There's a number that must have a symbol associated with it. Well, what's the units? The units are meters per second. Well, that's a distance per time. And I know distance per time is like my speedometer. So you should think speed or velocity. And since I'm only giving you technically the magnitude, it could be speed or velocity. It doesn't really matter. But in principle, we only have, one equation for speed, and we got a butt ton of equations for velocity. Uh, so we're going to assume that that 27.8 meters per second is the velocity, and you don't even know if it's the initial velocity or the final velocity. But upon reading the question a little further, oh, that should be the final velocity it has just as it gets to the end of the runway if the runway is just barely long enough. So then you see, oh, we must be taking off from rest. So I'm going to immediately write down solution, and I'm going to start writing down the quantities that I'm given. So I know the initial velocity is 0, and that's just something that I inferred and the problem implied. So keep that in mind. The final velocity is supposed to be 27.8 meters per second. The acceleration is supposed to be equal to 2.00 meters per second every second, which you can actually write as meters per second squared, but you should definitely say it as meters per second per second. So that's what I'm looking for in part A is 150 meters enough? So that's part A. And part B is if that's not, how long is. So I'm going to write down some equations here from kinematics. We know, for instance, that velocity is equal to velocity 0 plus AT. Now, that could work because I have a V final, which is the same thing as just plain V, and I have a V initial, which is V0, and I have an acceleration, but time doesn't seem all that relevant to me, so that one's not going to be very helpful. But we also have uh, v squared is equal to v0 squared plus 2ax minus x0. Well, the x minus x0 could be the length of the runway, and that would tell us basically, given the acceleration and the initial velocity, that would tell us how fast it's going at the end. And if the speed isn't big enough, then we know it's insufficient. Okay, so that's something else we could use. There's another kinematic equation, x is equal to 1 half at squared plus v0t plus x0. But again, that one needs a time, so that's not very helpful. So what I'm thinking is we're going to use the v squared equals v0 squared plus 2ax. Now, there's a couple ways you could solve it. You could solve it and assume that the final velocity is 27.8, and that would give us the distance required. You could solve for x minus x0, that's delta x. But that's sort of doing part one and part two all at the same time. So I'm going to try to do the problem like they meant. I'm going to see what is the final velocity if I assume that I only have 150 meters of runway. So for part A, for part A, I'm going to do this. V squared is equal to V0 squared plus 2A delta x. So this is going to be equal to 0 meters per second squared plus 2 times 2.00 meters per second every second times 150 meters. So you can see when you do this that 2 times 150 gives you 300, and 2 times 300 gives you 600. So that's 600 meters squared per second squared is equal to v squared. Therefore, the final velocity will equal the, in this case, I'm choosing the positive square root of 600 meters squared per second squared. And if we compute the velocity by computing the square root of 600, then our answer gives us, I gotta find my square root button, square root of 600 is equal to 24.49 meters per second is the final velocity. And that tells us no, 150 meters is not sufficient. Okay, so that's our answer to part A. It's 150 meters is not sufficient. And for part B, we want to know how big is a sufficient driveway, or how long is a sufficient runway. I don't know why I said driveway. In this case, we're going to solve for delta x though. So I've got v squared is equal to v0 squared plus 2a. Actually, I'm going to still call that delta x instead of x minus x0. So I'm going to write it like that. Now, normally, I try to solve my equations symbolically before I put the numbers in, and that's a good practice. I'm a theoretical physicist. That's what I prefer to do, and that's very useful if you can learn to do it. But sometimes students aren't that good with algebra. I would say do your best to try to learn how to do that. But if you can't get it by the end of the second semester of Physics 241 and 242, then maybe that's just okay. All right. Maybe when you get further along, you'll figure out how to do it better. But that's just a goal you should try to aspire to. But until then, you can just stick the numbers in and solve how you want. Now, if I wish to solve for delta x, what I'm going to do is subtract v0 squared from both sides. So I get v squared minus v0 squared is equal to 2a delta x. Now I'm going to divide both sides by 2a. And when I do that, I get delta x is equal to v squared minus v0 squared over 2 times a. So now I'm going to plug this in. Only this time I know the final velocity needs to be 27.8. So I'm going to write 27.8 meters per second for the final velocity minus 0 meters per second for the initial velocity square, and I'll square that, and then 2 times 2.00 meters per second every second. Now you can see when you square the 27.8, that's going to give you units of meters squared per second squared, and then you're going to divide that by meters per second squared, so you're only going to get basically meters out, and that's what we expect. So if I take 27.8 and I square that, I get 772.84. Now I'm going to divide that by 2 times 2, which is really 4. So dividing 772.84 by 4 gives me 193.21. So I get 193.2 meters is the minimum length of the runway. So, in order for us to design a runway for this type of plane, then we need to make sure the runway is at least 193.2 meters, or roughly 194 meters. And similarly, the answer for part A was no. Any questions on that? All right. This says estimate how quickly an airbag must deploy to help protect a driver traveling at 60 miles per hour, which is 100 kilometers per hour, which we just learned was 27.8 meters per second. And B, how does the seatbelt help? Okay, so with this one, what we have to do is this is an estimate problem, so this is one of those ones that's sort of like one of the Fermi calculations. But what we're thinking of is a car running into a movable object. So that could be represented by a huge, wall that's built so strong that the car, even at high speed, is not going to barrel through it. It's not going to knock it over. It's not going to even move the wall. We're wanting to imagine it hitting a movable object. So, like a huge tree or a huge wall or even a Mack truck fully loaded, possibly going the other direction, because you could, make a Mack truck that's not moving the same direction as you. If it's just sitting still, you might be able to make it move a little bit, and that would be more give than we want to account for. So you might have to actually imagine it hitting it at the same speed of you or even just a little bit less so that it would come to a stop. But either way, the main principle is we have this car sitting here and it's going to run into something. Let's say this is the car, and it's going to run into something like this. Boom. Okay. Well, the way cars are designed nowadays, and I just noticed this because, for instance, somebody ran into the back of my car yesterday and just, in a parking lot, not anything very fast, but it ended up causing about $3,000 worth of damage just because the car is designed to crumple instead of the human crumpling as a result of the collision. So what you can imagine is when this car is coming towards this immovable object, that everything from the front bumper of the car, the instant it touches that wall, up to, let's say, the back edge of the hood, all that's going to get to crumble after the collision and before the person hits the steering wheel. Okay, and the steering wheel, the dash, the windshield, all that stuff is the stuff that's going to damage the person. So, what you want to do is make sure that whatever time period that is, from the instant the front edge of the car touched that wall to the instant that bottom of the windshield touched that wall, that's the distance it's going to travel. And however long that takes, that should be how long we should allow the airbag to inflate before it saves the person. In other words, if the airbag inflates after that, it's not going to be any good because the human's going to have already, impaled himself on the steering wheel, and then explosion that's kind of violent and dangerous is going to inflate a bag and bust the person apart. So that's not what we want. Okay. So with that in mind, what I'm going to do is assume that the car roughly has a length of 1 meter from the back edge of the hood to the front edge of the car. And we're going to say it's moving at 27.8 meters per second. And we then say, well, how long would it take to travel? Well, you know that as soon as it starts to hit that wall, it's going to start slowing down. And you might even imagine that it's going to slow down to zero by the time it gets to the person, because that would sort of make the worst case scenario in terms of how bad the collision could be. So if we do that, then we can calculate the average velocity using, let's say, that average velocity formula that I told you that's only true when the acceleration is a constant, and then use that to figure out how much time you get before the wall that you hit has reached the windshield, which is where it's going to start to compress you or the driver or whatever. So let's start off with solution. So I assume delta x is equal to 1.0 meters. V0 is equal to 27.8 meters per second, and V final is equal to 0. Okay. What I want to figure out is T is equal to the question mark. So this is all part A. So what I could use is I could use V equals, no, I don't want that. Well, I could do that. I could say V is equal to V0 plus AT, but then I'd have to compute what the acceleration is. But I could use V squared equals V0 squared plus 2A x minus x0. I could use that to putting in the x minus x0 as 1 meter, putting the final velocity as 0, putting the initial velocity as 27.8, and use that to solve for the acceleration. Then I could take that acceleration and plug it in the first equation, and that would give me the time. So let's try that. So v squared is equal to v0 squared plus 2a. And again, I'm just going to call that delta x for ease. Now, what's that going to give us is the following. I'm going to say 0 squared is equal to 27.8 meters per second squared plus 2 times a times 1.0 meters. And this allows us to figure out that A would be, it's obviously going to be negative, but we're only going to care about the magnitude. But what we're going to do is take 27.8 and we're going to square that. That gives me 772.84. We learned that earlier. Now I'm going to take that and divide it by 2 times 1, which is just 2. And therefore, we're going to get A is equal to 386.4 meters per second every second. So that's what the acceleration would have to be. Obviously, I'm only using at best 2 sig figs, so those who are not sig figs, but that's our acceleration. Now, with that in mind, I could solve for t, and v equals v0 plus at implies t is equal to v minus v0 over a. So let's see what the t comes out to be. The t is going to be the final velocity, which is 0 minus 27.8 meters per second divided by negative 386.4. And when I do that, I'm going to say 27.8 divided by 386.4. And that gives me 0.0719 seconds. And since we're estimating, really, even 2 sig figs is too much. So what I would conclude is that we need to make sure this airbag can deploy in 700ths of a second. And that actually happens to be the same answer your author got. Anybody have any questions on that part?
It looks like
Yes.
one chat. Oh,
Go ahead, Christopher.
Yeah, my question was, why is delta X 1 meter? Like when you're stopping?
So what I was picturing is the hood of the car is about a meter long, and the car is going to be compressed over that 1 meter, and that's the time you have for the car to say, "Oh wow, I'm in a collision. Let me deploy my airbag and make sure it's out in time that the person can be caught by it, and actually experience the slow deceleration that comes from hitting an airbag as opposed to the fast deceleration that comes from hitting a steering column." Does that make sense?
Yeah, thank you.
Okay. I think I heard Jonna or somebody else, a female, asking a question as well.
no, I was just gonna say that there was a question in the chat, but that it was
Oh,
super.
gotcha. Oh yeah, I see they did that. Our form sheet's going to be okay. Got that. All right. So part B, it says, how does the seatbelt help? Well, if you're not wearing a seatbelt, the airbag isn't going to be much good because your body can just slide right under the airbag, off to the left of the airbag, off to the right of the airbag, that sort of thing. Not only that, airbags are not all that safe just by themselves. So if you accidentally have an airbag deploy, that could be a problem. So wearing the seatbelt actually puts you a little bit out of harm's way in general to protect you from that in case the airbag deploys by accident. So for part B, I'm just going to write down seatbelt keeps the body, not to be morbid, but it keeps the body from missing the airbag, by going under the steering column and the airbag, or by going to the right of the steering column and the airbag, or to the left of the steering column and airbag, that sort of thing. Anybody have any questions on that? All right, here's another one. It says, how long does it take for the entire length of a car, length equals 4 meters, to completely cross a 26.0 meter intersection if the car accelerates from rest at 2 meters per second every second? So what I'm going to do here, just to give you an idea of what I'm talking about, is I'm going to draw an intersection. And let's say this is an intersection. And what we're imagining here is a car is sitting here, and the length of this car is 4 meters, and then the length of this intersection is 26 meters. What we want is the car to go all the way through the intersection, but then further on so that it's completely bypassed it. And therefore, we need the car to go a distance of actually 30 meters. Okay, so that's what we're really asking for here. Solution to this, we have some initial conditions. The initial velocity is 0. The final velocity we don't know, but we do know the acceleration is 2.00 meters per second every second, like that. And we know the distance traveled, which we might call delta x. We know that's 30.0 meters. Okay. What we want to know is how long does it take? So they want to know how many seconds does it take. So t is the question mark. Now, we're looking for an equation that has V0 in it, that has A in it, that might have delta x. Remember, delta x is x minus x0. So if it had x and x0, then it has the ability to have delta x in it. So can anybody think of one of those kinematic equations that would work here? I'm going to give it a little head start. I'm going to rewrite the equation in a slightly different form so that the left-hand side is x minus x0. And then the right-hand side is going to be 1 half at squared plus v0 times t. So now you see that this side is the delta x that we want, and we can go ahead and figure out uh, exactly how long that's going to take. So what I'm going to do is I'm going to put in 30.0 meters for delta x is equal to 1 half times 2.0 meters per second every second times t squared plus the initial velocity, which is 0 times t. So that term goes completely to 0, no big deal whatsoever. And that tells us that t is going to be equal to 2 times 30.0 meters divided by 2.00 meters per second per second. And then I take the square root of all that. You can see that I'm basically just taking the square root of 30, but you also can see that I'm taking the meters and divide it by meters per second per second. So that becomes just a plain second squared in the numerator. The meters cancel out. And then when you take the square root of second squared, you just get seconds. So the square root of 30 is equal to 5.47. So the time required is 5.477 seconds, which we only had 3 sig figs, so that's extra like that. And that is the answer to the question. Anybody have any questions on that? Okay, so that was equivalent to example 212 roughly. And what we're going to do now is we're going to try to find another problem to work just to give us a little bit more experience. The example 213 is an estimate problem and it's really good, but that's kind of long. I'm not going to give that to you in lecture, but I highly recommend you study it. So please study example 213 thoroughly. Okay. So I'm just not covering. It's not that not important. It's just it's a long, convoluted problem to follow. I mean, even reading it is long. So that's why I'm skipping on away from that one. Uh, let's go here to estimate example 214. So I'm looking now at a problem from your textbook, and it is example 2-14, and it's an estimate problem. I usually call it 2.14. But I'm going to read the problem to you, and I'll read it more than once, so hopefully that'll help you. It says two moving objects, a police and a speeder. Car speeding at 150 kilometers per hour, which is over 90 miles per hour, passes a still police car, which immediately takes off in hot pursuit. Using simple assumptions such as the speeder continues at constant speed, estimate how long it takes the police, the police car to overtake the speeder. Then estimate the police car's speed at that moment and decide if the assumptions were reasonable. Okay. So again, a car speeding at 150 kilometers per hour, which is over 90 miles per hour. So I'm going to say V speeder is equal to 150 kilometers per hour, passes a still police car, which immediately takes off. So I don't have to take into account any reaction time. We're just going to go on the assumption that the police officer sees the car pass by them and immediately hits the accelerator and takes off. So the a car speeding at 150 kilometers per hour passes a still police car, which immediately takes off in hot pursuit. Using simple assumptions such as the speeder continues at constant speed, estimate how long it takes for the police car to overtake the speeder, then estimate the police car's speed at that moment and decide if the assumptions were reasonable. So what we have to do is figure out what's a reasonable amount of acceleration for a police car to get. Uh, in general, 0 to 60. I don't know. I think 0 to 60 would be a nice fast car. 0 to 60 is like 4 seconds. Or nowadays, we even know, for instance, the Tesla Plaid got it under 2 seconds. So it's like 1.9 seconds flat that they can get from 0 to 60 in. But that acceleration is so huge, we can't really expect the police officer to be able to have that kind of car with that sort of acceleration and then accelerate the whole journey. Because if the car really takes off that fast, in order for it to keep that acceleration that high, the car is going to have to reach, several hundred miles per hour. And even police cars don't do, more than they probably don't even do anywhere near 300 miles per hour, much less whether they get close to 200 miles per hour. I'm not sure. But either way, that's sort of not reasonable. So, what we might think is a little bit more reasonable is maybe it goes from 0 to 60 in 5 seconds. And then that might be a little bit more reasonable acceleration to expect. And hopefully that it's taking off so fast with such a high acceleration that it can just accelerate the whole time at roughly a constant acceleration. Even though we know, in general, a car's not going to be accelerate constantly for a huge amount of time. So what I can do is say the acceleration is going to be delta V over delta T. So if I say that the car is going to go 100 kilometers per hour, which is 60 miles per hour, in 5 seconds, then that's going to be 27.8. Is that the? No, that's not. That's not the 27.8 was 90 kilometers per hour, I think. Let me look back here just to remember. I'm trying to make use of the figure. Yeah, 100 kilometers per hour. To actually convert it, you're supposed to take 100 and divide it by 3.6. Yeah, that's 27.8. So, okay, that was right. It was 90 was 25 meters per second. So 27.8 meters per second. And that's going to happen in 5.0 seconds. So this is our approximate estimate of the acceleration of the police car. So 27.8 divided by 5 gives us an acceleration of 5.56 meters per second every second. Now, that's just a rough order of magnitude sort of type calculation to estimate what the acceleration of the car is. It might be smart for us to, instead of it calling it the full 5.6, maybe we just call it 5 even or 5.5. That would be a little bit more moderate in terms of an assumption. So we can do something like that. But now what we need to figure out is exactly how long is it going to take for the police car to catch up with it if the police car is moving such that it started off at zero velocity but had a constant acceleration the whole time. So the position of the police car is going to be 1/2 AT squared plus V0T plus X0, and the position of the speeder, X speeder, is going to be basically just V times T, where V is equal to 150 kilometers per hour. And of course, the way we convert that is we know that 3.6 kilometers per hour is equal to 1 meter per second. So we can just take that 150 and divide it by 3.6, and that gives me 41.7 or 41.67 meters per second. So that's the velocity of the speeder right there. So this is going to be 41.67 meters per second times time. And what we need is those two to be equal to each other, because at that point the police car has caught up with the speeder. We do know that the initial velocity, of course, is zero, and we can always call the initial position zero. So now what we're going to get is 1/2 times 5.5 meters per second every second. Notice I rounded down just to make it a little more reasonable in hopes that it might come out better. That times t squared is equal to 41.67 meters per second times t. Clearly, this t is going to cancel out with that t, and I can get just plain t is equal to 2 times 41.67 meters per second divided by 5.5 meters per second per second. So that will give you seconds. So 2 times that 41.667 gives me 83.33. Now I'm going to divide that by 5.5, and that gives me about 15 seconds. So the time is on the order of 15 seconds. That's the answer. Now, to check it for reasonableness, let's see exactly how far or how fast the police car would be going at this time. In other words, if it literally did accelerate at that acceleration for the whole 15 seconds, which is extremely unlikely that any vehicle could keep a high acceleration for 15 seconds straight and hold it constant. But either way, let's just check and see. So now we're going to use V equals V0 plus AT, but V0 is 0. So now I'm going to say the final velocity of the police car when it reaches the speeder is going to be 5.5 meters per second times about 15 seconds. 15 times 5.5 gives me 82.5 meters per second. And of course, 82.5 meters per second is probably pretty fast, but let's figure out how fast it is. What I know is that 1 meter is equal to 100 centimeters. And what I know is that 2.54 centimeters is equal to 1 inch. And I know that 12 inches is equal to 1 foot. And I know that 5,280 feet is equal to 1 mile. So now I've converted it to miles per second. And then I have to do 3,600 seconds is equal to 1 hour. And that converts it to miles per hour. So when I look at this, I'm going to say 82.5 times 1,000, or excuse me, 100. Oops. 82.5 times 100 times 3,600. That gives me a really big number, like 29.7 million. Now I'm going to divide that by 2.54 times 12 times 5,280, and that gives me 184.5 miles per hour. So it's approaching 190 miles per hour. I would have thought that's not a reasonable speed for a police car to go, but your author seems to think that is a reasonable speed because he got the same answer, around 84 meters per second, which they called around 190 miles per hour. I will tell you that I did see a video this weekend with a Formula One race car that did some donuts at the start line while a Lamborghini, a pretty nice Lamborghini, took off at the same time and floored it. So it actually, the Formula One car was allowing the Lamborghini to get way ahead. Like, I bet you wasted a whole 15, 20 seconds or whatever. And the Lamborghini is going in excess of 290. It reaches, I think, a 300 miles per hour at one point. And then I think it was actually on a one of the tracks that they used, because it looked like it had set up for the tracks as opposed to the Autobahn. But yeah, come to find out, even before they got to the end of the Grand Prix type track, the Formula One race car had still caught up and blew by the Lamborghini. So it was pretty impressive. Of course, it could have been all AI. Who knows? It looked pretty real to me, but who knows? Anybody have any questions on this problem? All right, so that's somewhat reasonable, I think. What we're going to hear, though, is we need to figure out about how objects behave in free fall, and this is something that Galileo did, and it was even said that Galileo had went to show everybody that all objects accelerate at the same rate, because Aristotle was teaching specifically, thousands of years ago, he was teaching that the rate at which something falls was directly proportional to the mass or the weight of the object. So that, for instance, a 100 mile per hour, I mean, 100 kilogram object would accelerate twice as fast as a 50 kilogram object. So that was what we were living with and under prior to Galileo and Newton, and it literally sort of held science at bay for on the order of over 1,000 years. Somebody wrote in here. Cool. Yeah, I'll check that out, Michelle. So in this case, what we know is supposedly Galileo took two objects pretty heavy, but one markedly heavier than the other, took it up to the Leaning Tower of Pisa, dropped them, and saw that they landed at the exact same time when they were dropped at the exact same time. And that probably didn't really happen. We know that there was a lot of bureaucracy associated with Italy by that time, and there would have been paperwork and stuff for him even to get the right to go into the Leaning Tower of Pisa, and we don't find anything like that. Not only that, if he actually did the experiment, it would probably be inconclusive at best, because it would be really hard to tell and to limit the uh, effects of air resistant in such a way that it would be obvious that the two things landed at the same time. But I will tell you, his inclination was correct. It turns out that once you learn Newton's second law of motion, it makes perfect sense that all objects fall at the same rate if you ignore air resistance. And the reason why is they accelerate based on Newton's second law, which says that F is equal to m times a. So if you solve for a, you get a is equal to F times m. That means the acceleration and the force are thumbs up, thumbs up. That means if I double the force, then I double the acceleration. If I triple the force, I triple the acceleration. Now, it also means the acceleration and the mass are thumbs up, thumbs down. So, what that means is if I double the mass, I, I cut the acceleration down by two. If I triple the mass, then I cut the acceleration down by three, so on and so forth. Well, the other thing is that the actual weight of an object, which is the force that goes in Newton's second law here, that weight is m times g, where g is gravitational acceleration and the m is the mass. So if you take something twice as heavy, then the force is going to be twice as big. But guess what? The mass, which the acceleration is inversely proportional to, is going up by a factor of two as well. So both the force goes up by a factor of two and the mass under it goes up by a factor of two, so that you get the same thing as F over m instead of 2F over 2m, and therefore the acceleration, which is equal to F over m and also happens to equal 2F over 2m, are the same. So it is perfectly correct to say that if you ignore air resistance, or if you can get rid of air resistance, then the acceleration is a constant. Galileo actually did this with inclined planes. He basically allowed an object to roll down an inclined plane. His reasoning being that he couldn't tell, they didn't have really good clocks back then, so he couldn't really tell when you drop something, does it fall at a speed instantly or does it slowly speed up to that speed? And really being able to figure out how long it falls was really an onerous task that you couldn't do with the timepieces that they had. But he reasoned that if he imagined something rolling down an inclined plane, that the vertical motion would be one component of the motion in general. You'd have a vertical component and a horizontal component. And if the inclined plane was very gradual, then the vertical component could be so small that you could measure it. And he ended up making up a clock that was very specially designed for doing these types of experiments. And it was a water clock. So basically, what he would do is when he'd go to drop a ball to roll down an incline, he'd open up a stopcock or a valve, and water would start to pour out of this tank into a pre-measured cup. And then when the motion stopped, he would turn the valve off and he would have caught a certain amount of water. Then you can go and weigh that water, subtract the weight of the actual container, and that water's weight would be proportional to the amount of time that elapsed. So he couldn't necessarily tell how long a single roll down the incline was, but he could obviously tell when the roll down the incline took twice as long, because the water for that measurement would be twice as heavy as the water for the other measurement. So that's what he ultimately did. And he was able to figure out from the laws of physics that are some of the laws of physics that we now use, specifically what we now call Newton's first law of motion, was originally Galileo's law of inertia. All right, so what we found out that acceleration is basically all objects, oops, all objects in free fall have the same acceleration at any particular place, or at any one particular location on Earth. And the reason I wrote it that way is when we learn about gravity, the force of gravity, we'll learn exactly how to calculate gravitational acceleration, and it depends on the distance from the center of the Earth to the altitude at which the object is falling as to what the acceleration of gravity is. So, for instance, if you went down to the bottom of the Marianas Trench, which is around essentially the lowest point on planet Earth, and you measured g, you'd find out that gravitational acceleration down there, instead of being 9.80, is maybe a little bit closer to 9.81. And if you went to the top of Mount Everest, which is the highest point on Earth, you'd find that the gravitational acceleration up there is a little bit closer to 2.79, or excuse me, 9.79 instead of 9.80. At sea level, this acceleration is A equals G equals 9.80 meters per second every second, which is also about 32 feet per second per second. Okay. So if you're just wanting a rough order of magnitude calculation, you can say the acceleration due to gravity is about 10. That's a really nice, easy number to work with. But if you want more specifics, you should probably use 9.8 if it's fairly close to sea level. And you notice that you're not going to be punished too much if you use 9.8, even at the height of Mount Everest, because it's literally on the order of a percent, 1% difference. So it's no big deal there. So, with this in mind, that all objects accelerate at the same rate, we might ask certain questions. So, I'm deviating from the examples in the book because I didn't find them that helpful. I want you to understand what's going on here. So, I'm just going to make up some examples on the fly. Uh, how fast is an object traveling after 1.00 seconds, 2.00 seconds, and 3.00 seconds if dropped with negligible wind resistance or air resistance. Your Some authors call it air drag too, so that's another way I can say it. So I'll just call it air drag. So in this case, we want our kinematic equations, and we know we're starting it from rest, and we know we have an acceleration, and we know we would like to know the velocity at some time later. So this makes me think that the best kinematic equation to use is V is equal to V0 plus AT. And since we're dropping it from rest, specifically, we know that because it was dropped. When it says something's been dropped, that means you sort of passively let it go as opposed to forcing it with any kind of speed or anything. So you have to infer from that that the initial velocity is zero. So with that in mind, that V0 is zero. And now what we see is V and A are thumbs up, thumbs up. What makes them thumbs up, by the way, is when V and some other variable are on opposite sides of the equal, but the same side of the fraction bar, then they're thumbs up, thumbs up. So V and A are thumbs up because they're both in the numerator. There's no fraction there, so you can just put them over one. That's how you know they're in the numerator. But V and A are on opposite sides of the equal. Now, you also see that V and T are thumbs up, thumbs up. And what that means is thumbs up, thumbs up. Actually, I should have put the hyphen between the two sets of words instead of between these first two words. Thumbs up, thumbs up. Okay. So that means that if T goes up by a factor of 3.19, then the velocity goes up by a factor of 3.19. Now, if it was t squared, then it'd be a different calculation, but it'd still be thumbs up, thumbs up. I'll show you that in a second. But that tells us that there's multiple ways we can solve this problem. So what I'm going to do now is I'm going to say v of 1.00 seconds is equal to 9.80 meters per second times 1.00 seconds gives me 9.80 meters per second. So that's the velocity after 1 second. Now, you could use the fact that it's thumbs up, and say, oh, well, if I double the time, I must double the velocity. So that would tell me that the new velocity is going to be 19.6. If I triple the time, then I'll triple the velocity. So the new velocity would be 3 times 9.8, which is 29.4, something like that. So I'm going to go ahead and show it the calculational way, but remember that other way is kind of nice too. And it teaches you something conceptually. So this is 9.80. I'll leave the units off this time. And you can see that it's clearly 19.6 meters per second at 2.00 seconds. So that's our second answer. What about at v at 3 seconds? So that's supposed to be 3 times 9.8, which is exactly right because the formula says 3 times 9.8. And 3 times 9, of course, is 27. And then 3 times 8 is 2, or 3 times zero point 0.8 is 2.4. So that'd be 29.4. Oops, left off my 2. So that's how the acceleration works on a object that's dropped from free fall, dropped from rest and is in free fall. It goes 9.8 meters per second after 1 second. It goes another 9.8 meters because that's why I told you to read the 9.8 meters per second every second that way, is because it tells us, hey, this acceleration is going to cause the velocity to change by 9.80 meters per second each second it travels. So after 1 second, it's went from 0 to 9.8. After 2 seconds, another 9.8 has been added to it. That makes it 19.6. And after 3 seconds, another 9.8 has been added. That makes it 29.4. Now what we want to do is say, how far will the object have traveled after 1.00 seconds, 2.00 seconds, 3.00 seconds? Okay. In this case, we still have A is equal to 9.80 meters per second every second. We still have V0 is equal to 0, but we want to know X slash delta X. We can use X is equal to 1/2 AT squared plus V0T plus X0, and we can either pull the X0 to the left and call that whole thing the delta X, or we can just call X0 0, which is what I'm going to do. We already know the initial velocity is 0, so I'm going to call that 0 as well. Now what we see is X and T squared are thumbs up, thumbs up. Notice I'm using an abbreviation now because I don't want to write that word over and over. They're thumbs up, but it's bigger than that because now if t goes up by a factor of 2, then x goes up by a factor of 2 squared, which equals 4. If t goes up by a factor of 3, then x goes up by a factor of 3 squared, which is 9. Okay. Similarly, 4 would get you 16, 5 would get you 25. So x of 1.00 is equal to 1/2 times 9.80 meters per second times 1.00 seconds squared. That's going to give you 4.90 meters. X of 2.00 is going to be 4.9 times 4. Well, 4.9 times 4 is 16 plus 3.6, so that's 19.6. And lo and behold, that's the same thing you get if you did this calculation, meters for that one. So again, 4 times 4.9 gives you 19.6. So we see that. And then X for 3.00, that's going to be 9 times bigger. 9 times 4 is 36. 9 times zero point 0.9 is 8.1. So 36 plus 8.1 should be 44.1. And that's how we're doing it sort of conceptually. But if we wanted to just brute force calculate it, we'd say 4.9 times 9 gives us 44.1, just like I said. Now, the neat thing is the equation here shows the V0t term and the 1/2 AT squared term. They're totally separate. So if I were to throw this ball down, then the V0t would do its own thing, like the particle's just moving at a constant, 2 meters per second if I threw it down at 2 meters per second. So it's always going to add that extra distance. So at 1 second, instead of it being 4.9, if I had thrown it down with a velocity of 2 meters per second, then it would be at 6.90 meters. Again, if I did that for after 2 seconds, then it wouldn't be 19.6. It'd be 2 times 2, which is 4 additional meters, added to the 19.6. That would give me 23.6. And similarly, if I wanted to calculate what would happen, again, throwing it down at 2 meters per second, after 3 seconds, it would still go the 44.1 as a result of the gravitational acceleration, but it also go 2 times 3, which is 6. So that'd make 50.1. So try this for V0 equals positive 2.00 meters per second. And then you could also try G or A equals G equals negative 9.80. So now we're going to consider making down the negative direction and up the positive direction. And we could then take the velocity initially to be positive 3.00 meters per second. If you did that, what you'd see is it's trying to go up. So it would go up as if no acceleration would occur. After 1 second, it would have gone a distance of 3 meters. But because acceleration is acting downward on it, that would be subtracted. That 4.90 we got before would be subtracted. So it would actually be 3 meters up minus 4.9. That'd be negative 1.9 meters after 1 second. And then after 2 seconds, it'd be, again, something similar, but this time it's 2 times 2 would be 4. So it'd be 4 minus 19.6, so on and so forth. But that's it. We've covered everything from chapter 20 or chapter 2. So you guys are free to go. If you haven't already chatted me your first and last name, please make sure you do. Remember, you do have a test that is due Sunday. And that's really only on chapters 1 and 2, but that should be plenty of time for you to do that. Did move the homework to give you a little bit of time Tuesday to get it done, but I think the test being done due on February 1st is still fine. I might change it. I'm not sure, but I'm not leaning towards it. Have a good one, everybody. Thank you for coming.
Thank you. Have a good night.
You too.
Thank you.
Thank you.
Thank you, Professor.
Thank you. Hayden, did you have a question? Okay, it looks like everybody's done. So thanks again for coming. Bye bye.